So our next speaker is from academia. She's Magdalena Balazinska, and she's an associate professor at University of Washington after she got her PhD from MIT. And she has been doing lots of work about data management and cloud computing. Her talk's title is Big Data Research, where industry solve all the problems. So let's hear Magda's view on this topic.
Right, good morning, everyone. So I'm the speaker between you and coffee, but actually the way the keynotes are working, I don't have to speak for another 40 minutes, so hopefully you will get to your coffee sometime today. I'm very happy to be here today, and when I was asked to follow up on Todd's talk, I thought, you know, oh my God, there's so much going in industry, it might be intimidating for us in academia, so let's tackle that problem. So as we heard in Todd's talk, everyone today has a big data problem. The data is large, the data is diverse. People often talk about it as a data lake. When the data is coming from these vehicles or other sensors where we then get data streams, and as we just heard, when comes time to actually work with the data, it might feel a lot more like a data swamp. But in any case, there is tremendous excitement in big data today. And this excitement is translating into an immense amount of activity in industry. So this slide shows one of those, big data landscape, pictures where each of the small icons represents the logo of either a product or an organization, and you're grouped in meaningful boxes. So there's one small box in the corner at the bottom that represents the Hadoop stack. There's another box a little bit higher up that represents our beloved parallel databases, another box on machine learning, and so on. And at this point, you should all be complaining that you can't read the slide. Well, I'm much closer to the screen, and I cannot read the slide either. It's just too crowded. So the big question is then, how can we in academia contribute to this exciting time of big data management? And this is not a talk of should I work in academia or should I work in industry, but instead, if for those of us who are in academia and thinking about writing our next grant proposal, picking our thesis topic, writing our next paper, how can we contribute to this exciting space of big data management systems? So what is really exciting is actually, as the VLDB community, we are, I would say, in a great position to contribute because we have a long history already contributing. So we have been working on big data much before big data was even a thing. So here's a screenshot of a paper from the very first VLDB, VLDB 1975, before many of us here were even born. And that paper already tackles the problem of distributed databases. And in fact, distributed databases were one of the main topics in the early years of VLDB. We had here, entire sessions on distributed databases, including distributed transactions, distributed transaction processing. And for those of you who have good eyes, you should be able to recognize some familiar names in these slides. Of course, another core tenet of big data management today is parallel data processing. Well, as we know, we have been working on this since, way before everybody else, late 70s, early 1980s. Here's a screenshot of a 1982 VLDB paper. And again, we had many papers on these topics, including multiple papers from the well-known Gamma project. And what I find interesting is kind of going over these old VLDB proceedings time after time. Almost every single hot topic in big data management today, we have already worked on it. Sampling, active databases, which are precursors to data streams, in-memory processing, so parallel shared nothing in-memory processing, semi-structured data, and I'm omitting many. They include data cleaning, data integration, iterative processing, and so on. But the big question then is, so what is next? Did we already solve all the big data problems in the 70s and 80s? Clearly, the answer is no, because otherwise we wouldn't have this big data landscape slide. So what else? Did we lay the foundations, and should we just let the marketplace take over? And I would say clearly not. We can contribute in many fundamental ways. But sometimes people can be intimidating. And one argument that I'm hearing is how can we do big data research in academia since industry has all the workloads? They have access to all these customers, all these clusters. They are very generous in releasing sometimes their workloads. We actually heard a very exciting announcement at the Symposium on Cloud Computing last week about Microsoft releasing some very interesting telemetry data. But this is a very small amount of information. My argument here is that we actually do have a lot of workloads right there on campus, and they are tremendously exciting. Astronomers need to work on tens of terabytes, even petabytes of telescope images. Earth scientists similarly work on satellite images. Almost all the scientists have very interesting spatiotemporal data. The picture on this slide shows a kind of a depiction of a universe simulation, which has tens of, even hundreds of terabytes of multidimensional data. Genome scientists need to operate on these ridiculously large matrices. And approximately almost everyone on campus has some kind of large graph that they need to operate. So we have these exciting applications, and they are about exciting topics: understanding the nature of the universe, curing cancer. These are all very exciting topics with customers right there together with us on campus, and they are running their clusters, trying to process this data so we can analyze this cluster, something we did in a recent VLDB 2013 paper. The other thing that is very exciting about these on-campus applications is that the requirements are going much beyond what we have been doing in the 70s and 80s. Today's applications need novel machine learning. They need iterative data cleaning, iterative processing. They need graph analytics, et cetera. So very exciting applications. And I think the first way that we on campus can contribute to big data management systems is by seeking out these applications and working with them. In some cases, people may worry, well, if I work with scientists, won't I be, just setting up their Excel spreadsheets and doing kind of, grunt work for them? I would say don't do that. Find a scientist who is excited to build a new tool with you and try to apply that tool to their problem. And that is where I think really the innovation will take place. So the second argument, though, is, well, but industry has all the tools. If we look at Google, Microsoft, all the other companies, they have the exciting large-scale tools. So what can we do? Well, we have access to open source tools. So one thing that we can do directly is to take open source tools today and apply them to these exciting applications in academia. This is something we have done several times in our group, and I'm going to just give you one example. So as one example, we were working with these astronomers who are simulating the universe since almost the Big Bang until today, and they had one seemingly simple type of analysis. They said we have one snapshot of the universe. We want to cluster the particles to find the galaxies and other structures. Seemed very simple. We implemented this in both Hadoop and Dryad. And the algorithm was simply, well, let's break the space into smaller partitions, find clusters within these partitions, and then reconcile clusters within partition boundaries. This seemed to be very simple. When we applied it to one of the early snapshots of the universe, we got great performance. When we applied it to a later snapshot of the universe, we got terrible performance. And the question was why? And here's the answer. The answer was in data skew. So as it happens, the universe becomes increasingly more structured over time. In this picture, on the x-axis, we have processing time, and on the y-axis, we are showing all the tasks that we are executing. The red ones are finding the clusters locally. The blue ones are merging these clusters across partition boundaries. And as you can see, a few of the tasks at the top are taking a completely disproportionate amount of time. And the reason was that the clustering algorithm had this kind of n-squared complexity, but only in very dense regions. So what can we do about this? Clearly, we can use a different clustering algorithm, and this is one thing that we did. But as systems builders, what can we do to make it easier? It shouldn't be that hard to get good performance. So we did several things as a result of applying open source tools to these scientific problems. The first thing we did was to build just a progress estimator. Can I have a tool that actually tells me how much time remains for my DAG of MapReduce computations? And this work, the lead student on it was Christy Morton. We then built a more powerful tool where we could ask questions. Why did this Hadoop job run so much slower than this other MapReduce job, even though it actually processed less data? And this was work led by Nodira Kusainova. We then addressed the skew problem. So can we build a system that manages the skew either statically or dynamically in these skew reduce and skew tune systems? And this is work that was led by Yang-Chul Kwon. And of course, our community has been doing work on skew handling before, but here we were looking at these MapReduce type of environments. And finally, we also said, let's go beyond explaining the performance, making it better, but can we make Hadoop faster at more complex type of processing, such as iterative processing in our Hadoop system? And this work was led by Yingyi Bu and Bill Howe. So I think this is exciting. I would actually pause here and say, if anyone is starting as an assistant professor, this is probably the fastest way to write a paper that has a lot of citations. Take an open source tool that exists today, apply a real workload to it, find how it breaks, make it better. But I think that we can be more creative. And to be even more creative, I would say we should follow in Mike Stonebreaker's footsteps and actually build our own systems. And this is something we build in our group. So in the database group at UW, together with the eScience Institute, we built a tool called Myria, which is a new stack for big data management and analytics. At the bottom, we have a shared nothing parallel query execution system, which is kind of a very efficient processing system. On top of it, we have a query optimizer that is also a federator. So one thing we can do in Myria is I can start to run a query in the Myria X query execution engine, then continue inside DB, then come back and continue my processing in Myria. And if you think this is exciting and interesting, please come to our Big Dog demo, which is right after the coffee break. And the last important thing about Myria is that we are running it as a cloud service for our users on campus. We actually have a cluster deployed, a production cluster, a users mailing list, and we have users actually accessing this. So why is this important? Why build yet another big data management system? This is important because whether we do become the next system that takes over the world or not, this frees us completely from all the assumptions made by existing systems. Let me give you two examples. So as one example, I mentioned we built the Hadoop system before to make Hadoop better at processing iterative computations. Iterative computations are also at the heart of Myria, but Myria is a new system. So we can completely rethink how we're going to do iterative processing. So one thing we decided to do was to support both synchronous processing, where we do one iteration, block, everyone stops, everyone waits, and then we do another iteration, and also asynchronous processing that has been shown by others to be very efficient for many applications. In this case, all the machines in parallel just keep producing, keep finding new facts, and keep aggregating the information until we converge. So in Myria, we can support both because we are building the system from scratch. At the same time, we decided that we definitely still wanted users to have a declarative interface to the system, something that is easy with synchronous processing, but becomes much more challenging with asynchronous processing because we have to worry about when applications are still correct when we execute them asynchronously. So here we used a subset of data log with aggregation, which is a great way to reason about queries, although our users actually express the queries in kind of SQL with extra constructs. And finally, when we started to apply these different iterative processing techniques to the real applications from the previous slides, we found that asynchronous is not always faster, sometimes is not. And when it is faster, it is often faster only if we do asynchronous right by doing kind of the right kind of prioritized processing on the data. And if you think this is tremendously suspenseful, then please come to Jingjing Wang's talk tomorrow afternoon when she will give you all the details about why and how all of this works. I mentioned that we also run Myria as a cloud service, but I'm not going to have my users come and pick from one of 50 different instance types and telling them to say how many instances they want, what kind, should they be memory optimized, CPU optimized. Users should not have to worry about this. As we operate Myria as a service, what we show to our users is something different. We tell them, just show us your schema, tell us how much data you have, and we show them something that we call a personalized service level agreement, where we say, given your data, really your specific data, Here are the kinds of queries that if you run these types of queries, we will guarantee these runtimes for you. If you want to run other queries, then there's a different runtime for a certain price. If you're willing to pay more, then we can have much better guarantees on the runtime. Again, we call these personalized service level agreements. The details are in our CIDR paper, which was led by my student Jennifer Ortiz. And this kind of describes the pipeline of how to generate these PSLAs. So this is, I think, tremendously exciting. We can start with these on-campus applications, apply existing tools to them, make them better, build our own tools, and be creative in what we are doing, creative in advancing the state of the art. But in some cases, this can still be a little bit intimidating. Sometimes people don't want to be in this heart of this race. There's a great quote from someone who attended SOG. He came to me and said, Magda, I think big data management systems are just too much of a bloodbath. And I said, well, maybe, but maybe it's fun to be part of the bloodbath. But if you don't want to be part of the bloodbath, there's actually much more to big data management than usability and performance. We can actually go and look much beyond to the problems that might not be the main ones that everyone is working on today, but problems that will become important in the future. Let me give you 2 examples of projects that we have been doing in this space. So the first example was, imagine that we solve performance. Big data management is fast. Imagine that we solve usability. Big data management, it's also easy. Well, what happens next? What happens next is my data sometimes is data that I produce. More often, it's going to be data that I'm getting from somewhere else. And there are different challenges that comes with it. First, in some cases, I might actually have to pay for the data. The Azure Marketplace is a great example. It's a service online where buyers can go and actually purchase different types of data. And this is a screenshot of one of the data sets and the kind of suite of prices that come with it. The question for our community is, how should we be pricing this data? The seller knows, economists understand the value of data. They can specify different price points for different views on the data. But if a buyer comes and they want to purchase a very special kind of personalized data product, can we automatically derive the price for that data product for them from the different price points set by the seller? Or do we need to resort to manual negotiations, which clearly won't scale? So this is work that we have been doing in the query market system, and that work was led by Paris Koutris. The second question is, even if the data comes for free, and definitely when the data comes with a price, it will be accompanied by a license agreement. Today, these license agreements look like a wall of text written by lawyers. Often it's actually, I think, copy-paste from Word without even any HTML tags. It's just pasted there. I don't want to read it. I won't read it. I'll just click fine, and I won't worry about it. But if I'm an organization, I have to worry about it. It's important that if someone gets data, they do respect these license agreements. And this is an important problem. And today, all we can do is just train the users, make sure that they do understand the limitations of what they can or cannot do with the data. But can we do better? Can we replace this wall of text with a declarative specification of the license? Can we build a system that will automatically enforce these licenses and do so with minimal overhead so that the users are not even aware that anything is happening unless they are about to violate an agreement, in which case we want to explain to them why and how? And this is something that we have been working on in the context of the data lawyer system that was led by my student Prasang Upadhyay. So I think there's just tremendous excitement in what we can do in academia related to big data. The final, though, complaint that I hear is, well, industry has all the engineers. They have teams of 20, 50. How can we compete? We don't compete. We provide the engineers. So I would say this is almost our responsibility to do research in big data management such that we can produce wonderful students. And here's an example of students who have worked with me and done PhD thesis in different aspects of big data management, and then have gone on to have tremendously successful careers in academia. So in conclusion, I would say that we live in just tremendously exciting times. It's the best time to be a database person, to work in big data management. There is a lot of excitement and a lot of activity in the industry. I think that just makes things more interesting. There are many ways in which people like me and several of you in academia can contribute to it by leveraging the workloads that we have access to on campus. And of course, we can also collaborate with industry. This is just a complement to that collaboration. We can leverage open source tools. We should build our own tools to be creative and try to be disruptive. And we can also look ahead at other problems that others perhaps don't have the cycles to look at yet. And most importantly, we are educating the next generation, which is, I think, one of our most important responsibilities. So I'm going to stop here, make sure we have time for discussions, questions, and coffee. And I'm going to acknowledge all the hard work of our students in the database group, our collaborators in e-science and domain sciences, and of course, our sponsors. Thank you.